Okay, everybody, welcome to chapter 10. Now, this one is going to require some note taking, so make sure you have either printed out these PowerPoints or have a notebook beside you or your 3x5 cards. We're going to look at confidence intervals for the difference between two means. We're looking at independent samples, so one does not have an effect on the other. So distinguish between independent and paired samples. Construct the confidence intervals for the difference between the two population means and describe the pooled standard deviation and the known standard deviation methods. So first we're going to distinguish between the independent and paired samples. A drug company has developed a new drug that is designed to reduce high blood pressure. The researchers wish to design a study to compare the effectiveness of the new drug to that of the old drug. So here's one way that the study can be designed. You have two samples of the individuals are chosen. One sample is given the old drug and the other sample is given the new drug. After several months, blood pressures of the members of both samples are measured. We compare the blood pressures with the first sample to the blood pressures in the second sample to determine which drug is more effective. This design, the samples are independent because one does not influence the other. The other way we can do it is a single group of individuals is chosen. They're given the old drug for a month, then their blood pressures are measured, then they switch to the new drug for a month, after which their blood pressures are measured again. This produces two samples of measurements, the first one from the old drug and the second one from the new drug. We compare the blood pressures in the first sample to the blood pressures in the second sample to determine which drug is more effective. In this design, the samples are paired. Each observation in one sample can be paired with an observation in the second. Let's look at constructing these confidence intervals for the difference between the two population means. So imagine that we're going to compare a new drug to reduce blood pressure to a standard drug. We will draw two independent samples. The first will get the new drug and the second will get the standard drug. We can imagine that these samples are coming from two populations, a population of patients who take the new drug and a population of patients who take the standard drug. For each population, there is a mean reduction in blood pressure. We are interested in estimating the difference between the population means. So we're going to let mu1 be the population mean reduction for the new drug and mu2 be the population mean reduction for the standard drug. We want to construct the confidence interval for the difference. So what we are looking at is as we would say before, what's the difference between these two drugs? That's actually what we're doing when we say there's a difference. We are subtracting them to see if there is a difference between the new drug and the standard drug. So the point estimate for the difference is the difference between the sample means. So in other words, this difference is the difference in our samples that we chose. So the difference between the two drugs for this experiment is going to be the difference between the two samples. So the sample means x bar sub 1 and x bar sub 2 have variances, which are the variance of the population divided by n, which is our sample, and the variance of the population of the second divided by n sub 2, which is the number in our sample. So when the samples are independent, the variance of the difference can be known to be the sum of the variances. I'm going to say that again. When samples are independent, the variance of the difference can be shown as the sum of the variances. So in other words, the variance of the two sample means, the difference between the two sample means, is going to be the population variance divided by n plus the population variance of the second one divided by n sub 2. So n sub 1 and n sub 2 just means they're the two different groups. The standard error of x bar sub 1 minus x bar sub 2, or the difference between the sample means, is the square root of the variance. We don't know the value of the variance sub 1 and variance sub 2, but we approximate them with the sample variances from our sample that we drew. So that would be standard deviation squared sub 1, standard deviation squared sub 2. So therefore, the standard error would be, when we're adding these two together, we're going to take the square root of that to find our standard error. So the critical value for the confidence interval is going to be t sub alpha over 2 based on the student's t distribution. There are two ways to compute the number of degrees of freedom: a simple method for computing by hand and a more complicated method by using software and calculators. The simple method is the degrees of freedom will equal the smaller of the n sub 1 minus 1 and the n sub 2 minus 1. So the smaller one. The margin of error is obtained by multiplying the critical values and the standard error. And the standard error. So we're going to take that t alpha over 2 times the standard error. Yes, I know these formulas are starting to look complicated, but you know what each one of these symbols mean. So let's just try to logically look at what that is. So the confidence interval is constructed by adding and subtracting the margin of error from the point estimate. So you're going to take the difference between the two means, add or subtract the margin of error. This method is often referred to as Welch's method. I'm sure named after mathematician Welch. So the method we just described requires the following assumption. We have simple random samples from two populations. The samples are independent of one another, and each sample size is large, which is greater than 30, or its population is approximately equal. So here we go again. A drug company developing a new drug designed to reduce blood pressure. To test the drug, a sample of 15 patients is recruited to take the drug. Their systolic blood pressure are reduced by an average of 28.3 with a standard deviation of 12. In addition, another sample of 20 patients takes the standard drug, and the blood pressure in this group is reduced by an average of 17.1 with a standard deviation of 9. Assume that the blood pressure reductions are approximately normally distributed. Find the 95% confidence interval for the difference between the population mean for the new drug and the standard drug. First, we check the assumptions. We have two independent random samples, and the populations are normally distributed. The assumptions are satisfied. So now we're going to find the difference between the sample means. We get 11.2. The degrees of freedom by the smaller one, which is still 14 because both of them had 15 in the group, right? Oh no, take that back. This one had 15, this had 20. So we're going to take this and minus 1. So 14 is my smaller. And my degrees of freedom, now that we just said is 14, at a 95% confidence level, we will obtain the value of t sub alpha over 2 of 2.145. So we're going to take a look at this standard error. We're going to figure this out, bringing this square root over top of both of them. Add these two together, and then we get 3.6946. The margin of error would be t sub alpha over 2 multiplied by this standard error. So I get 7.925. And my 95% confidence level will be that difference between the means plus or minus the margin of error. So it's going to be 11.2 plus or minus, that's 7.925. So my range is going to be, for my difference of my means, from 3.3 to 19.1. So given that, we're 95% confident that the new drug provides a greater reduction in systolic blood pressure and that the improvement due to the new drug is between 3.3 and 19.1. Now, if you construct a confidence interval for the difference between the two means with technology, you get somewhat a different answer than you'll get using the method we presented. The reason is that computers and calculators compute the degrees of freedom differently, using a more accurate but more complicated formula. So most computers and calculators compute the degrees of freedom as follows. So they're going to take this value divided by this value divided by the first sample n sub 1 minus 1, so the degrees of freedom of the first, and then the second one, our variance divided by n, also divided by the degrees of freedom of the second. I will have to say, thinking that's an error again. Let me double check. These errors in these things are really getting on my nerves. So let me take a look here. Let's go to 10.1 before I go further. Okay, almost there. Okay, constructing using technology. Yep, it should be n2, so right here this should be n sub 2 minus 1, so this is the second one, so make sure you change that on your PowerPoint. All right, let's continue. So here we have our technology. We're going to put in our 2 sample t integer. We're going to hit stats, we're going to put in our statistics, and then we'll get our 95% confidence interval at 3.3 to 18.8. You can see that's a little bit different than what we got before. All right, objective 3, describe the pooled standard deviation and the known standard deviation. In most situations in practice, Welch's method is the method of choice for constructing the confidence intervals for the difference between the two means with independent samples. There are 2 other methods that are sometimes used, and they're often not the best in practice, however, so we will always use Welch's method. So first you can use a pooled standard deviation when the population variance of both of the populations are known to be equal. And then we would use a z sub alpha over 2 when the population and variances are known. When the population variances of the first and the second are known to be equal, again this should be 2, are known to be equal, there is an alternate method for computing a confidence interval. This alternate method has widely been used in the past, still an option for many forms of technology, but it's not recommended. And the problem is that the method that the assumption that population variances are equal is very strict. The method can be quite unreliable if you use this when the population is not equal. Population variances are not equal. All right, so if we have a level, and here again, this is our 1 minus our probability, then when you multiply it by 100, you're changing it to a percent. Confidence interval when the standard deviation of the first and second are known. We're going to take the differences between the sample mean minus our z times our standard error, so our our variance over our number in our first sample plus our variance over our number in our second sample. So that subtract here and here, add here is going to be the actual difference between the population means is going to be between one of these two. Now, they also note that this is the same as Welch's, except for the sample standard deviations are replaced with the population standard deviations, and that T alpha over 2 is replaced with RZ alpha over 2. So what you should know from this one is the difference between independent and paired samples, how to construct a confidence interval for the difference between the two population means, the pooled standard deviation method, and the known standard deviation method. And this would be all for 10.1. We're going to do 11.1 next, and then we'll go back and forth between 10 and 11. Talk with you soon.